Hi, welcome to Lab 4, Road Lab. In this lab, we'll examine the motion of spring mass system in which the mass flowing in an arc while oscillating on the spring. And we also will understand and predict the motion by using Tracker and Python along with the Newton's second law and the energy principle. So we will specify the force interacting with the system, and in this case, we will have the spring force and the weight force. And at first, the mass is in static equilibrium position, and then the mass is pulled to the left side and then released from rest. And the mass positions oscillate in two dimensions, left and right along the x-axis and forward and back along the z-axis. So we will begin analyzing the motion of the mass by using Tracker. We've set the length, the scale length, to be 0.7 and the time to be timescale 10.5 seconds, the origin to be the attachment point, and the mass was released at frame 5. So that's going to be where we start our analysis because that's when the objects start moving. And the data that we collected here, we will be copying and pasting it to the ICSV file, and we'll later use to compare with the predicted motion that we find in Python. So in Python, we start plugging in what was given, the mass and the gravity, and then plug in the initial values we got from Tracker. And the mass, since the mass was released from rest, its velocity, initial velocity is 0 meters per second. Then we need to calculate the period of oscillation, t. And Tracker tells us that at 8.167 seconds, the mass already oscillated 5 times. So we use that number to divide by 5 and we get a time for each oscillation period. So this is the equation that we need to use to find the stiffness, spring stiffness, which is K. And we know T and everything else we know. So K, we will compute that to be 5.95. We then use the concept of equilibrium that we discussed earlier, meaning that the net force is 0. So the magnitude of the weight force equals the magnitude of the spring force. So we can see here equilibrium, the net force is 0, then they equal. So then with that, we can find the relaxed length because we already know K. Then our relaxed length is going to be 0.0377 meters. Then after that, we use Newton's second law to find the new velocity and then new position. The calculations are given right here. And when we run the program, we can see that the blue arrow represents the spring force, which always points up, and the black arrow represents the weight force, always points down. This means that the spring force is always longer than its natural length during the entire motion. The weight does not change in magnitude, but the spring force does. It gets longer and shorter as the mass oscillates. The net force should therefore become negative when the spring force gets shorter and positive when the spring force gets longer. And then we get into the energy principle where our choice of system is mass, spring, and earth. And the energy principle stated that the change in total energy system equals to all the energy transfers with the surrounding. So in this case, there are no interactions that transfer energy to and from the surroundings. We neglect a little small effects such as the air resistance. So the total energy here is 0. So we know that kinetic energy is 1/2 mv squared, the gravitational potential energy is mgh, and the spring or elastic potential energy is 1/2 ks squared. So before graphing the energy change, we know the arrow representation. Change in kinetic energy is blue, change in potential energy, elastic, is red, change in gravitational potential energy is green, and change in total energy is yellow. So as the mass oscillates, the energy oscillates as well. So when we run the program, we can see that both the gravitational potential energy and the spring potential energy oscillates with the same period. And the energy changes have the same magnitude but in different signs, meaning that as the spring potential energy increase, the gravitational potential energy decrease, and vice versa. And some observations pertaining to the change of kinetic energy is that it oscillates pretty much twice as fast as the potential energy changes do. And we can see that the yellow arrow representing the total energy change is 0, just as we expected, based on the energy principle we've discussed. So we didn't include the CSV file we got from Tracker earlier, and then we run this program. The red ball is the observed mass position, and the blue ball is a predicted mass position. We can see here that the red ball is a little jumpy due to the difference in the delta t in Tracker and Python. Because in Tracker we set it to be 10.5 seconds, while in Python it's like 1/210 seconds. So for the questions, we pretty much answered the first one already. The energy principle stated that the total energy E equals to all of the energy transfers with the surroundings. And because in the graph that earlier, that yellow arrow represents the sum of all the energy changes is 0 for the entire motion, because there's no transfer of energy here since we neglected like air resistance. So therefore, the principle and energy principle is satisfied. And for question number 2, the period of oscillation for X position, we've collected that from Tracker is 1.6334 seconds, and for the Y position from here is 1.6524 seconds. So we compare these two values together, and the difference between these is 1.1565%. So that means that these two values are fairly close to each other, and it's a very small percentage of difference. This could cause from human error